Okay, so today I will be going over the second set of synthesis practice problems from Chapter 12. In these problems, we are given a reactant and a product, and we need to figure out what mechanisms and reagents to use in order to get the product shown. Each problem will require multiple mechanisms to get the desired product. So let's get started and take a look at Part A. Here we have a bromocycloheptane, and we want to turn it into 1,2-cycloheptanol via an anti-addition. We'll start by using some sodium methoxide. This will create an E2 elimination reaction, letting us both get rid of the unneeded bromide and create an alkene. Alkenes are much more reactive than alkanes, so this opens up many new possible mechanisms. We'll use this to trigger an alkene epoxidation by introducing peroxyacetic acid. Then, by simply adding some water, the oxygen in the epoxide will take one of the hydrogen atoms. This will open up the epoxide, allowing the newly formed hydroxide anion to bond with the now available carbocation. The two alcohol functional groups will want to be as far away from each other as possible, so it'll end up being an anti-addition. And there we have it, simple as that. We have a 1,2-cycloheptanol that we are looking for. Part B gives us a 2,3,4-trimethyl-3-pentanol and wants us to make a ketone and 3-methyl-2-butanone. So wait, we need to turn one molecule into two? How on earth do we do that? Well, if we look hard enough, we can already see the two shapes we need in the molecule. Here and here. We just need to once again get rid of what we don't need and create that all too helpful alkene double bond at the place it needs to be split. This time, we'll use sulfuric acid in an H2O solution to get the job done. With all the hydrogen atoms floating around freely, the alcohol will grab one and pop off. At the same time, a water molecule will grab a proton from a carbon adjacent to the new carbon, or to the new carbocation, and the leftover electrons will come to form a double bond. Now that that's done, we can perform ozonolysis to cleave the double bond. This will cause it to form a malozanide, shift around to rearrange itself, and then just form an ozonide. Finally, we can use either zinc or DMS to reduce it. We'll just use zinc this time, and it'll steal one of the oxygens, causing the other two to form double bonds with the carbons we need. Now, if we take a step back, we'll see that this creates a ketone and a methyl-butanone, what we were told to make. The third problem, C, has us working with 3,4-dimethylpentanine, or pentine, and wants us to create 4,5-dimethyl-2-hexene. This one's actually pretty simple. We'll start by using sodium amide to deprotonate the terminal alkyne. Now that it has a negative formal charge, we can elongate the chain by using a simple alkyl halide. Bromomethane seems good. When it's brought into the solution, the alkyne will grab the methane, popping off the bromine in the process. Then, all that's left to do is use sodium and ammonia to perform an alkyne reduction. This is a bit of a complicated process, so I won't go too in-depth about it right now. Just know that the end result will reduce the triple bond to a double bond, giving us exactly what we needed. This brings us to the final problem, D. In it, we're given methylcyclopentane, and we simply need to make 2-methylcyclopentanol. This may sound like an easy thing to do, just adding an alcohol group onto it. But it involves a couple pretty complicated mechanisms. And we're going to be starting it out heavy by using bromine and some light to perform free radical bromination. To do so, we use light to trigger the initiation by separating some of the bromine molecules into bromine radicals. This will then propagate by turning the carbon that methyl is attached to into a radical, causing it to take bromine from another bromine molecule, turning the other into a radical. This will continue on and on until the bromine radicals eventually find each other, terminating the mechanism. Now we just use some sodium ethoxide to eliminate the bromine and form the well-needed double bond. Finally, we're going to do what's called hydroboration oxidation. The first part of which will be done by simply adding boron to the solution. The alkene will go ahead and grab the boron, while the tertiary carbon will grab the now free hydrogen. This is repeated until boron is bound to 3 cyclopentanes. Now we add hydrogen peroxide and sodium hydroxide to make hydroperoxyl. This process is also pretty complicated, so I won't be going too in-depth here about it. But just know that in the end, we end up with the 2-methyl cyclopentanol that we needed. I hope this video has helped you see that there are many different mechanisms at your disposal for trying to synthesize molecules, and that the best way to do it is to just take it one step at a time.